I will turn it over to you.
Thank you, Michelle. Hi, everyone. I'm Parimal. I work in the Engineering and System Performance Group at RF. And today I'm going to present on navigating the challenges of increased penetration of inverter-based resources, IBRs, in our grid today. And I'll mostly focus on challenges with modeling and bulk electric system stability analysis. Next slide. So this is my main crux of the presentation. So why are we here? So we are seeing consistent increasing levels of penetration of IBRs in the North American grid. And at the same time, we are also observing increased retirement of thermal and other conventional resources. So the need of the hour is a more detailed analysis to identify reliability concerns. In today's presentation, I'm going to talk about a number of recent IBR disturbance events that involve control malfunctioning or protection malfunctioning, resulting in trips and a lot of megawatt loss. I'm also going to talk about dynamic modeling practices in terms of how are we modeling IBRs currently in our dynamic studies, and what are the software platforms that are being used to perform these studies. At the end of the presentation, what we'll get out of this is we need better data gathering, we need better model benchmarking and studies at the interconnection stage of these IBR generation units. Yeah, that's pretty much the crux of my presentation. Next slide. So these are the key terms or acronyms I'll be using throughout my presentation. I thought I'll put a separate slide for it. So first one is PLL. It's called. I'll just go over them briefly. First one is PLL, phase lock loop. It's a pretty popular term when we talk about IBRs these days. It's just a synchronization mechanism which synchronizes these IBRs currently existent or in the queue IBRs to the grid. It locks the IBRs to the grid. PSPD and EMT, when we talk about performing dynamic simulations for a bulk electric system, we are typically talking about one of these two simulation ideologies. PSPD is called positive sequence phasor domain. Popular software tools like PSSE and PSLF, which are pretty much industry standard tools, fall under this category. The main advantage of these software platforms or this software philosophy is that we are able to run extremely large power system networks and run dynamic analysis on these systems, bulk electric systems. And EMT, which is the other type of simulation philosophy, which is a short form for electromagnetic transient, is a more detailed simulation platform where you can get more granularity in terms of what you want to see in terms of the phenomena. And the shortcoming here is that as of now, currently we don't have a computationally enhanced platform where we can run an interconnection wide case. It's predominantly used for very specific areas of the footprint where we might have some specific conditions that exist and we want to see a certain phenomena in more granularity. GFL and GFM are two technologies of IBRs. Most of the current installed and in the queue IBR generation falls under the category of GFL, which is grid following. Basically, these IBRs use a synchronization mechanism to lock to the grid or synchronize to the grid, whereas grid forming IBRs are the ones that is a more recent or modern IBR technology, and it's being pushed these days or nowadays because of its similarity or a similarity in performance to conventional machines. So the thought is that these IBRs are more suited to an environment where we have an IBR rich grid, where these type of IBRs can provide similar support and performance as conventional machines. I'll talk briefly about these in one of my future slides. So, and SSR is subsynchronous resonance. It's a specific type of oscillatory phenomena that happens in series compensated lines rich system where you have a lot of series compensated lines. And it has been seen when a lot of these IBR resources are interconnected to POIs that fall in the neighborhood of these series compensated lines, there is this unique phenomena that happens where oscillations are seen in the system. These type of events have been reported in Texas as well as in WEC. So yeah, so that's these are all the terms I'll be using. Next slide. So this is a picture of IBRs in the queue across North America, and then broken down across each ISO. So the first image on the left top is basically tier one and tier two queue generation across North America. So as before I move further, tier one and tier two are two categories of queue generation. Tier one are the queues that are already under construction or have met all the milestones as part of the interconnection process, and tier two are the generation queue that are still under study and they are still in the process of moving along the interconnection process. So as you can see in the top left image, most of the queue generation as of now is solar, followed by battery and natural gas. If broken down by each of the regions, top right image shows that PJM and MISO have almost double or triple tier one queue generation for solar, which is a significant amount. And if you look at the bottom left image, which is the wind generation in the queue across different ISOs, you see again PJM and MISO have significant wind as part of the tier one queue, even though you can see a slowdown there in terms of interconnection. Solar sees a lot of growth, but wind is seeing a slowdown as seen by these plots. Similarly, in the middle, you have the battery energy storage that has a lot of that forms a lot of tier two queue in PJM. Now, obviously, a lot of this tier two queue will not see the day of the light because a lot of these queues might drop out, but still it's a significant amount, around 45 gigs in PJM. So yeah, I mean, a lot of battery in the queue as well. And the last image is the offshore wind. Again, a lot of offshore wind, around 30 gigs is in the tier two queue. As mentioned earlier, a lot of these might fall out of the queue, but still a significant amount. Next slide. So this slide shows generation retirements into the future till 2034. So these are all conventional retirements, which is primarily thermal and nuclear. As we can see, as we go on till 2034, we are seeing around 120 gigawatts of conventional generation retirements. And on the right, we see this broken down across each of the ISO. And as you can see, MISO and PJM have top two confirmed plus unconfirmed generation retirements, which forms a great base for rest of our presentation. So in short, we are seeing an increased penetration, increased IBR rich generation in the queues, and at the same time, we are seeing a lot of the conventional generation, primarily thermal and nuclear, retiring. So as we can see, we'll face a number of challenges going into the future as far as performance of the bulk electric system is concerned. Next slide. So now moving on to IBR dynamic models. So this slide typically talks about the typical models that are used as part of dynamic studies in modeling these IBR resources. The first category is positive sequence phasor domain standard library models. These are standardized models, which means they don't differ across manufacturers like GE or Vestas or Siemens. They're standardized models. The main reason why they became popular many years ago is because they are not black boxed. They don't have any proprietary information, so the user has the freedom to go through the parameters and tune the parameters and see what parameter is exactly causing some issues. So it's easy to debug They became popular several years ago. But a challenge is that there is no one-to-one mapping between these model parameters and the real equipment. So there is, in terms of identifying issues when going from what's observed on the field or in real equipment and then what's in the model, there's no one-to-one mapping. So there's a challenge in identifying what exactly went wrong in the modeling. As per NERC recommendation, these models are best suited for IBRs outside of a local study area. The second category is positive sequence phasor domain user-defined library models. These are models that include some or all of equipment's code and logic. These are exact models that replicate the hardware on the field. These obviously differ across vendors, which means a user-defined library model from GE will be different than Vestas and will be different than Siemens. So they will have different models. And they are typically black boxed, which means the users don't have access to the internal structure. They only provide the black box model. And the NERC recommendation is that these are best suited for representing IBRs inside a local study area, which means if you're running a study in your footprint or in your TO footprint, you use these models to represent the IBRs in your footprint, and then the remaining area, you use the standard library models. And the third category is the electromagnetic transient models. These are the most detailed models. They pretty much replicate exact phenomena that happens on the field. And the NERC recommendation is that they are best suited for highly localized studies, such as if there's a weak portion of the system that needs more in-depth analysis, or if there's a portion of the system that has a very high IBR penetration, then some certain phenomena like control interactions between these IBRs are possible. And in those scenarios, EMT models are more suitable and provide a more exact, detailed, or more granular response and results. Next slide, please. So this is a slide that just briefly shows what are the time scales that we are looking at in terms of phenomena and what are the tools that are suitable for those time scales. As is evident from the slide, EMT is suitable for observing or analyzing extremely fast transients, which some happen as a result of control interactions, or in certain cases in weak grid conditions. Whereas stability of small signal tools such as PSSC and PSLF, which fall under the category of positive sequence phasor domain tools, are tools that are used for bulk electric studies, that are used for typical transient stability, small signal stability, and frequency stability studies. So this slide is just a brief representation of the time scale of dynamic phenomena. Next slide, please. So before I move further into my slides, so the challenges that I'm going to talk about today in terms of IBRs, I'm going to break it down into three categories. One is challenges due to model inaccuracies that have been recently identified as part of NERC efforts. The second is challenges associated with the right software platform that is being used, whether we are using the right software platform to analyze certain dynamic behavior. And the third type of challenge is the challenge associated with inherent physical characteristics, which means these IBRs are inherently different in terms of physical characteristics as compared to a conventional machine. So there are challenges associated with that. So these are the three categories that I'm going to talk about today. This is the first category, which is the challenges due to model inaccuracies. Next slide, please. So these are recently reported IBR disturbance events. There are a few of these that I've put in this table, but there are a few more. And the crux is that we have in this table, we can easily see that we have events that have resulted in a loss of around 1700 megawatt of IBR generation. And a couple of events which are the Odessa events got a lot of fell under a lot of scrutiny some years ago, because a lot of these trips or megawatt losses were a result of maloperations which were not expected. So I'm going to talk about those IBR performance issues in the next slides. Next slide, please. So these are the root causes that were identified as part of these event postmortem analysis. These are a lot, and I would need a separate presentation for this. But just to summarize these, basically, a lot of these events happened as a result of controller maloperation, which means these IBRs have controllers controlling frequency and voltage. And in a lot of these events, these controllers were too aggressive, meaning that they pushed in too much reactive power at some point and resulted in over voltages, and which resulted in spikes and these inverters or IBRs eventually tripping. And a lot of these events were also caused by PLL losing synchronism. As I mentioned earlier, PLL is a device that is used to synchronize these IBRs to the grid. Under disturbance conditions, a lot of times these PLLs lose synchronism, and that resulted in a lot of these IBRs tripping. And then a lot of these megawatt trips were due to something known as momentary cessation, which has been mandated, not necessary now, and it should not be a part of any of the dynamic models as per NERC. But momentary cessation was a feature where these IBRs were able to limit their output to 0 megawatts, even being connected to the grid, which means they don't trip, but they have the ability to basically take their output to 0 megawatts and still stay connected to the grid. So this resulted in a lot of megawatt loss under these events and essentially a lot of issues. So next slide, please. So NERC recently released a level 2 and level 3 alert in relation to these IBR performance issues. And the key findings that they observed was that at the time of interconnection, the generation owners, which are the GOs, did not have accurate or exact facility data late into the interconnection process, which means they were using approximate models to represent their IBR dynamic models, as well as their collection systems, which are the transformers and the tie lines that are part of the project. So this was one major issue that was identified. And a lot of the other issues were related to the voltage and frequency write-through settings. These are certain protection settings that are part of the IBR models, and their main goal is to ensure that these IBRs write through disturbances, which means they don't trip under disturbances, but only within a band. So there is a well-defined region of that's called a no trip zone, where these IBRs are not expected to trip. And outside that zone, these IBRs obviously should trip to protect their equipment, to protect their inverters and the hardware. So it was identified that a lot of these IBRs had wrong voltage and frequency write-through settings. And a lot of these IBRs were also identified to have incorrect PLL loss of synchronism protection settings, which means, again, a wrong setting or incorrect setting in terms of how these protection systems should have been set up. So next slide, please. So as part of the NERC recommendations out of the level 3 alert, these can be broadly categorized into two main categories. One is performance criteria requirements, and the other category is model accuracy requirements. So NERC recommended that in terms of performance criteria, NERC recommended that each of the TOs and TPs in conjunction with the PC should come up with specific performance requirements that they desire or require from these IBRs, which means they should have specific requirements as to how these IBRs should help in terms of voltage and reactive power control. Like, how should they provide reactive power to the grid in times of disturbance or faults, how they should support the grid. Similarly, how they should, IBR should support the grid in terms of frequency events, what exact frequency performance requirements are needed from these IBRs, and what exact write-through settings should be used for these IBRs, so that incorrectly or they write through when they are needed to support the grid. And then also there should be very explicit post-disturbance requirements, which means how fast do the TOs and TPs in conjunction PCs require the active power to recover active power of these IBRs and voltage of these IBRs to recover after a disturbance. There should be very specific requirements on these specific criteria: active power, reactive power, and voltages. Next slide. In terms of model accuracy, NERC identified, as mentioned in a few of my previous slides, a lot of these issues that were observed were because of incorrect models being used as part of the studies, as opposed to what was observed on the field. In fact, in the Odessa Odessa event postmortem analysis, was identified that a lot of issues that were observed on the field were not could not be replicated in a simulation environment using the models that were submitted at the interconnection stage. So it was a lot of these events. What came out was that the models that are being used during the interconnection and study process are not really adequate in terms of how they replicate the on-field behavior. So NERC recommended to have a specific model verification and validation test and reporting to be done from the TPs and PC side. And what that would entail is to benchmark the positive sequence phasor domain models, which is PSSC models or PSLF models, and EMT IBR models against actual measured responses. So these models have to be benchmarked against actual responses for a number of different disturbance conditions. And these requirements are specifically set for IBRs that are in the queue and are being studied under the interconnection process. And for operational IBRs that are already operational and already operating on the field, their performance has to be compared against the models that are currently existent based on the previously existing criteria that was in place when those IBRs went through the interconnection process. The NERC recommendation for GEOs, which are the generation owners, is to ask for model validation and benchmarking reports from inverter and power plant manufacturers. So inverter manufacturers like SMA, Power Electronics, Tesla, they should provide these generation owners with benchmarking reports showing that their inverters the inverter models do replicate what their hardware does. So that was one of the recommendations that NERC laid out for the generation owners. And then there should be a change management process from the Geo side where they track any firmware changes that happen throughout the life cycle of the IBR. So these were the main two model accuracy requirements that came out of the NERC level 3 alert that happened recently. So next slide, please. This is a sample table of a model validation test, which is specifically known as model quality test in ERCOT. So this table shows what tests does ERCOT require as part of the interconnection process for the GEO to perform, and they want the benchmarking to be performed against field measurements for both PSSC and PSCAD models. They're looking at okay, what happens if there's a big fault or disturbance that happens in the system? Do the IBRs, the models that are being used for these IBRs, do they really replicate what would happen on the field using measurements? And then same thing for small voltage and small frequency disturbances. What happens if there's a small disturbance? Does the performance really benchmark against what would happen in the actual hardware? So this is just a sample table of requirements that is needed in ERCOT currently. Next slide, please. So this is the next few slides will talk about simulation platforms and the challenges associated with it. Next slide, please. So as I mentioned earlier, these are the two mainly existent dynamic simulation philosophies that exist in our grid today. Positive sequence phasor domain, which is PSSC and PSLF-like tools, and EMT, which is PSCAD. Essentially, that's the most popular EMT tool. And what is the applicability of each of these? So basically, under weak grid conditions, which is when there's a portion of the system connected to long transmission lines, and there's not enough synchronous generation or conventional generation that region, that portion of the system might become weak. And if that region has a lot of IBR rich generation, then EMT simulation has shown to be more accurate in terms of representing some nuanced phenomena that happens that positive sequence phasor domain software tools were not able to capture. Unbalanced conditions. So EMT simulation is directly suited for running scenarios where there are unbalanced conditions on the grid, because positive sequence tools don't have the access to all three phases. So it's by default, EMT is the most suitable study in that scenario. And if you have IBRs that face unbalanced conditions, grid conditions, then EMT is the obvious tool to go. DC side dynamics, so all of these inverter-based resources, specifically solar and battery, they have a DC side to it, which is typically not represented in tools like PSSE and PSLF. EMT tools do have the ability to represent these DC side dynamics. So anything to do with DC side dynamics, obviously EMT is the right tool to go, and that would provide you the right granularity in what you're looking for. Next slide, please. Subsynchronous resonance, as I mentioned in one of my previous slides, is a very specific phenomena that happens when IBRs interconnect close to a series compensated line. And this again is this phenomena can only be observed in EMT-like tools, because the frequency involved is not, it cannot be represented in a positive sequence software tool like PSSE or PSLF. Time scale. So EMT, as represented in one of my previous slides, EMT has the capability to represent very, very fast dynamics, which in certain cases might be because of extremely fast controller operations of these IBR units, or certain other dynamics. So EMT is able to represent extremely fast dynamics, whereas positive sequence phasor domain tools are not capable of representing very fast dynamics. They are only for electromechanical scale dynamics. So the recommendation is that positive sequence phasor domain tools are still the recommended tools for bulk electric system studies with improved IBR models. EMT tools are recommended when there are some localized type of studies that need to be done, need to be performed, such as control interaction in weak grids, SSR, analyzing unbalanced conditions. So that's pretty much the recommendation for using each of these software tools. Next slide, please. So this is a table that kind of tabulates all the root causes that were identified as part of the IBR disturbance events that I showed a few slides ago. So this table shows which of those phenomena could have been represented or studied in each of these software tools. And as you can see, certain phenomena such as instantaneous AC overvoltage and overcurrent tripping, DC bus voltage unbalance, and inverter over and under frequency could not have been analyzed in positive sequence phasor domain tools like PSSE, whereas EMT would have been able to analyze and study these phenomena. So as evident, EMT does find a place when the analysis requires it, or what you're looking for is very specific to what EMT would cater to. So yeah, this table basically shows, yeah, EMT analysis is definitely needed in certain situations. Next slide, please. Now this is the last portion of my presentation, which is challenges due to inherent properties of these IBRs. Next slide, please. So IBRs have very little inherent functionality resulting from their physical form, which means they don't have a physical rotor like a conventional machine. So they don't provide the services like a conventional machine would do. Most of their the services that come out of the IBR are defined by their control algorithms. So it's a fully controlled, governed performance. Since they don't have any physical, a lot of physical mass, they don't provide inertia to the system, which is obviously a very long discussed topic when it comes to IBRs. IBRs don't contribute a lot of short circuit current as compared to conventional synchronous generation, which and the implications of which are there are deeper voltage sags and slow voltage recovery after disturbance events. And this also presents challenges with respect to relaying and protection coordination due to very small short circuit current contributions. Next slide, please. So most of the current installed IBR based generation, which is wind, solar, and battery, they're based on grid following technology. Grid following technology essentially requires synchronization to an external grid, as I mentioned, through a PLL, to tightly control active and reactive power outputs. It cannot control system voltage and frequency by itself. It needs an external resource for that. It's not able to maintain stable output, as I said. If the PLL falls out of synchronous during grid events, it's not able to maintain its active and reactive power output, which results in eventually in the IBR tripping and essentially megawatt loss from the system. And these kind of IBRs face challenges under weak grid conditions, and that's how it became popular, because there were certain phenomena that were observed with these grid falling inverter technologies and weak grid conditions that essentially kind of brought EMT analysis to the forefront a lot of years back. Now, recently, there has been a push towards a new technology termed as grid forming IBR technology. Unlike the grid following, they don't need a synchronization strategy to synchronize to the grid. They can regulate their own terminal voltage and frequency. They can emulate inertial response similar to conventional machines, but they require some active power headroom to do so. They can operate under weak grid conditions. They don't have, they don't fall short under weak grid conditions similar to the grid following inverters. They have the capability to black start a system, which is not the case with grid following technology. And as far as transitioning from grid following to grid forming is concerned, is only a software tweak as far as PV and batteries, IBRs are concerned. So next slide, please. So these are all the recent current activities that have been going on in NERC as part of the FERC Order 901. A lot of these standards concerned with write-through requirements and the disturbance reporting requirements. So I have these listed here so that if someone wants to go through these in detail, these are all here. Next slide, please. So the key takeaways are essentially the model in recent IBR reported events, model inaccuracies have been the major driver. As part of NERC recommendations, model verification and validation requirements need to be established in order for these models to replicate what the actual hardware is doing in the field. Due to computational constraints, positive sequence phasor domain-based tools, which are essentially PSSE and PSLF, are still the practical option for analyzing bulk electric system dynamics with these IBRs. EMT analysis is necessary only for very unique specific system conditions. And the grid forming technology seems to be the future for a grid with increased IBR penetration. Next slide, please. That's it from my side. Thank you. I'll wait for any questions if anyone has any.
Thank you so much, Parimal. That was very informative. A lot of great information there. And we're receiving questions coming in throughout your presentation. And so I think as you got closer to the end, you might have answered some of these. So let me see if I can kind of sort through what I think maybe we still need to hit here. The first question, for projected 2027 and beyond increases in IBRs, do you have any sense if there's any double counting between regions of what we think we will actually have interconnect on the system?
I don't, Michelle, I don't have the exact information. I took that right out of the NERC LTRA 2024 report. So I don't have any information whether there was any double counting that happened. Yeah.
Okay, yep, that's good. The next question is around grid forming versus grid following inverters. And I think as you got to the end, you answered the first part here. So going to the second part of the question, to your knowledge, are there any grid forming inverters installed on the system? Will we need a combination of both grid forming and grid following? And then the third part to the question is thinking about historic installations, can they be upgraded to grid forming if needed?
Yeah, that's a great question. So to the first question, whether there are any current installations of grid forming, so regions like Hawaii, so HECO, which is their utility in Hawaii, they require specifically grid forming inverters because, as I said, grid forming inverters have the capability to black start the system. They provide better system services in terms of how they support the system voltages and frequency. So in areas that are more islanded and not highly interconnected, grid forming inverters are more suitable. I mean, in terms of the mix, what I have read, and there's actually quite a bit of material from NREL on this. There was a report that kind of mentioned that 30% mix, 30% grid forming and 70% grid following is what they have come up with, which is based on their analysis that they ran, which was like they wanted to show that you don't really require 100% grid forming inverter-based penetration. You can have 70% of your fleet to be grid following and only 30% grid forming, and it will serve the grid well. So that's how it goes. That's how the mix can be. And in terms of if currently installed grid following can be converted to grid forming, based on the recent conferences and webinars I've attended, seems like it's just a software upgrade. Now, in terms of upgrading, I know a lot of times if there's a significant change in the model of a generator on IBR resource, there has to be a interconnection study that has to be redone to kind of see if there are any system impacts of those. So I don't know how the ISOs are going to handle such type of a upgrade during the operational phase. That's my gut feeling. So.
Okay, yeah, great, thank you. Moving on to the next question. Now, this question I think came in when you were talking about the NERC alert recommendations. And so the question is, why is it not recommended to use user-defined models for interconnection-wide studies and only for local area studies?
That's a great question again. So user-defined models, as I said, are black boxed. And a lot of times what these black box models means is that you essentially receive something called as a DLL, which is a dynamic link file. And a lot of times these models, if there are a lot of user-defined models in the system, sometimes there is a challenge in terms of initializing and working with these dynamic models because each of the vendors such as GE, Vestas, Siemens has their own DLL file, and sometimes they interact. And then because of these models being black boxed, the user does not have access to what's happening inside. So it becomes very complicated to debug these models. So NERC recommends that use these user-defined models only in your study area and not everywhere, because sometimes it becomes a challenge. Now, if these user-defined models obviously become evolve and become better and better, at some point that's the right way to go, to use user-defined models because they replicate they replicate actual hardware more accurately than standardized models. But there's some way to go there where these models are in good shape and don't have any interactions in terms of software and stuff. So
okay, fantastic, thank you. We do have a number of questions here. Let's try to get through more here. Next question, could a weak grid condition exist within a strong interconnected grid with lots of synchronous generation, such as what is seen in the Eastern Interconnect?
Did you say weak grid?
Yeah, could a weak grid condition exist within a strong interconnected grid?
No, I mean, typically not. But if you think about it, a good example is ERCOT, and ERCOT has a portion of the system which is known as the Panhandle, which has majority of the wind in there. And ERCOT Panhandle, I mean, ERCOT is a well interconnected system internally, not to the external grid, but internally they're well connected. And but Panhandle is kind of a remote area where there's no major load. So all of that power has to be transmitted over long lines to major load centers like Dallas, Austin, Houston. So because of that kind of a phenomena where you have long transmission lines carrying this power, that Panhandle system becomes a weak portion of the system. So it can happen. I mean, if something like, so if in our footprint, maybe something like a offshore wind kind of a scenario where there's a lot of offshore wind in some portion, and there are long transmission lines that are carrying this power over to the main load centers, that can create a weak portion of the system in that specific region. So yeah, it can happen in that scenario.
Okay, yeah, great answer. Thank you for the detail there. Next one, okay, seems like EMT modeling is better than the PSPD modeling. So why do PSPD modeling at all?
Yeah, because of the computational challenges. So EMT as it stands currently cannot handle a system as big as the Eastern Interconnect. So if any user has to run dynamic studies for a system as big as Eastern Interconnect, EMT would not be capable to handle it, or each contingency or each event would take 2 to 3 days, which is impractical. So computational challenges are the main restriction right now, and so that's why it's a lot of the studies that are being done using EMT platforms are very localized studies where there are a lot of IBR units, or there's a weak grid condition, or there is a risk of subsynchronous resonance. So only in those specific scenarios are the EMT studies more being used right now. So and obviously in smaller systems, like if you think about Australia and Chile, they have their detailed grid model in EMT, but they are smaller systems, right? So for them, computation is not really that big of a challenge. But for our system, Eastern Interconnect, it's not feasible as of now. So
great, thank you. Good explanation. I'm learning a lot from this Q&A here, so I really appreciate people putting in all these great questions. Okay, next one. Can you clarify what is inverter over and under frequency in your PSPD versus EMT comparison?
It's the same. It's the same. The tripping, yeah. So when we I know what's being asked. So in the postmortem analysis for these a lot of IBR driven events, disturbance events, it was observed that a number of these events had over frequency or under frequency trips, and the main driver for these trips was essentially a controller malfunction. So each of these IBR units comes with a voltage reactive power control loop and a frequency active power control loop. And what happens is under disturbance, the controller pushes a lot of active power based on the control logic that it has. And because it pushes a lot of active power, suddenly there is a spike in the frequency because they are interconnected. Active power and frequency are interconnected. So there is a spike, or there is a spike in the other opposite direction, and that results in instantaneous tripping of these IBR units. So it's essentially a controller logic malfunction that happens. So.
Okay, great. The next question, I'm going to combine two questions because you had some questions on the synthetic inertia, and you talked about this a little bit in your final slides when you were talking about grid forming inverters, which could make synthetic inertia possible with IBRs, right? So
Yes.
the question is, what did you mean when these IBRs can emulate inertial response but require active power headroom to do so? If you could elaborate a little bit on that.
Sure. So essentially, if we look at frequency events that happen in the grid, essentially, if we compare a conventional machine versus an IBR, when there's a frequency event, the first thing that restricts the drop in frequency is the rotor of the synchronous machine, because it's a huge inertial device or body, right? So it doesn't allow the frequency to change that much because of its physical form. So that's the main inertial response that we get from a synchronous machine or a conventional machine. Now, IBRs don't have that physical form or a physical device that does that, but they can replicate that behavior by injecting active power extremely fast, right? So in order for them to inject active power, they need to have headroom, which means if they're already operating at their Pmax, which is their max limit, they don't have any headroom to push any further power. So, but if they are operating at 80% limit, they have that 20% which they can push extremely fast, and that active power can arrest the drop in frequency, which is similar to what a conventional machine would do. But the concept is different, but the mechanism, how it's happening, is different. In one case, in conventional machines, it's the physical form of the rotor, but in IBRs, it's the ability to push active power extremely fast, because these are power electronically controlled devices, so they can push power extremely fast. So they can emulate inertial response in that fashion, but they need headroom for that.
Okay, great. That all makes sense. So along those same lines, needing that headroom, is there any thought of how much headroom you need, or any calculations or any sources of information for that?
I don't have exact numbers for that, but I can refer to an NREL study that has done this kind of analysis. I don't think they recommend a specific headroom, or I don't remember seeing any specific headroom, but I can refer to that study, provide that reference. Yep.
And then again, along those same lines, thinking about why maybe grid forming technology isn't being installed more, any thoughts or comments on how much more expensive it is? Is it 2 to 3 times more? We had a couple of questions on the expense of those.
I don't think there is based on my understanding, and I don't think there's a major cost implication. I think the major challenge was defining a performance criteria, or what exactly are we looking from these grid forming inverters. Like, we know they have these advantages over grid following, but then in terms of when they go through the interconnection process, what exact requirements do we set for these grid forming inverters, right? So that a lot of time was spent on clearly defining those, and clearly I think based on my understanding, the main concern was that we should clearly lay out what exact performance or performance requirements or system services do we really get from these grid forming IBRs to the maximum. Like, we analyze it to the level where we know, okay, we need these specific requirements from these grid forming IBRs. I don't think it's not a cost implication here. It's just people were studying this to an extent where they wanted to know all the aspects of what exact services can be achieved from these grid forming inverters. And I think now they're in good shape. Tesla already has a grid forming inverter that's being pushed out, and a lot of other inverter manufacturers as well. So.
Okay, so you talk about needing to study and come up with like a standard or standardized approach with it. Who's doing those type of studies? Is that like an IEEE or an EPRI? Who would be working on those studies that we could look to for more information?
So EPRI obviously is doing a lot of work on grid farming inverters and system services that would be required out of these grid farming IBRs. NREL, National Renewable Energy Laboratory out of Colorado, they have a lot of reports that talk about grid farming IBRs and specific performance enhancement that they provide over grid following inverters. So yeah.
Okay, fantastic. Thank you, Parimal. This was so informative. I appreciate you presenting here for us today, and thank you to our audience.